In this video, we're going to discuss hydrate structure in a little bit more detail, talk about how that relates to hydrate equilibrium. We'll look at reacting with radio-labeled water and seeing what's the situation there. We're then going to discuss more about hydrate and versus carbonyl energy and reactivity, and then do a few problems ranking carbonyls with respect to the percentage of hydrate that they'd form at equilibrium. So when we react an aldehyde or ketone with water and acid or water and base, we're going to generate a hydrate structure. And during hydrate formation, the delta H is negative, but the delta H is a pretty small number. Okay, and what contributes to that delta H being pretty small is the fact that we have these lone pair repulsions. Okay, each of those oxygens have two lone pairs. And remember, those lone pairs occupy physical space. And it's the clashing of those lone pairs with one another, having electronic repulsions, that would destabilize the tetrahedral structure here. And that could then, we could reduce those lone pair repulsions if we reform the carbonyl. But then delta H is negative, so we'd form our hydrate, and then we'd reform the carbonyl. So we get that back and forth and back and forth. But it would be the reactivity of the carbonyl that we begin with that would ultimately dictate if KEQ is greater than 1 or if KEQ is less than 1. So let's start off by saying that the more reactive an aldehyde or ketone is, the larger its KEQ would be, the more hydrate percentage we'd form at equilibrium. On the flip side, if you're looking at a series of structures, the least reactive aldehyde or ketone is going to form the smallest amount of hydrate, has the smallest KEQ. Now let's create a reference point for the cutoff point for where KEQ is greater than 1. The structure here, acid aldehyde, an aldehyde with just a methyl group, is your reference point for where KEQ becomes greater than 1. Anything less reactive than acid aldehyde would have a KEQ less than 1. That would mean that the carbonyl is favored and the percentage of carbonyl is greater than the percentage of hydrate. So acid aldehyde is our reference point, including acid aldehyde. Anything including that and more reactive than acid aldehyde will form a KEQ greater than 1. That means the hydrate is going to predominate in that equilibrium. And as we increase reactivity, we have an even larger KEQ value. Then anything less reactive than our cutoff point of acid aldehyde would have a KEQ less than 1. Small value, okay? And then the least reactive carbonyl has the smallest KEQ. The most reactive carbonyl will have the largest KEQ. What this means is that the presence of electron-withdrawing groups can help to increase the percentage of hydrate at equilibrium. And generally speaking, having smaller alkyl groups helps to form hydrate more favorably. On the flip side, if we had electron-donating groups, that would decrease the percentage of hydrate at equilibrium, as would having bulky alkyl groups, because bulky alkyl groups would destabilize the hydrate structure. Okay. This visual is very key for a lot of problems we'll solve. Before we do questions relating to KEQ and hydrate formation, let's think about using a radio-labeled water molecule. Radio-labeled water would have an O18 as opposed to regular oxygens, which would be O16. Now looking at this molecule here, notice how that is more reactive. It is more reactive than acid aldehyde, which means that assuredly here, KEQ should be greater than 1. That means that in this equilibrium of reacting with water and acid, we should expect to form a predominance of hydrate. The principal species at equilibrium will be hydrate. And notice specifically the principal species would have 2 radio-labeled O18s in the structure. Let's break that down. If we imagine going through the hydrate formation mechanism, the initial hydrate would have 1 O18 oxygen in the structure. But remember, we can reform the carbonyl, then generate hydrate, reform the carbonyl, then generate hydrate. So what can happen is after we generate the initial hydrate structure, that oxygen, which is unradio-labeled, could be protonated. That would create a water-leaving group. Then the O18 oxygen can collapse and kick out that water-leaving group, reforming a carbonyl. Then we're going to assume that in this reaction, we're using an excess, a large excess of the radio-labeled water. And what that's going to then favor here is that radio-labeled water attacking and bonding. We would then have to deprotonate the oxygen atom here. And as a result of that, we would form our hydrate with 2 radio-labeled oxygen atoms. And again, it's because of the reactivity of our starting carbonyl that tells us that KEQ is going to be greater than 1, we will form a predominance of hydrate at equilibrium. And with the radiolabeled water, assuming a large excess of that, the predominant species at equilibrium is a hydrate with 2 radiolabeled O18 oxygens. The initial structure would just have 1, but we can then protonate the unradiolabeled oxygen, form a protonated carbonyl as we eliminate that from the structure. And because the reactivity is ultimately favoring hydrate, radiolabeled water attacks and adds in, we then will deprotonate and we'll form our hydrate again, and that will be the species that predominates at equilibrium. Now imagine that we react this carbonyl here with radiolabeled water and acid. We're going to assume in excess of the radiolabeled water. Because of the inherent reactivity of this carbonyl, KEQ for this reaction would be less than 1. That means that the hydrate will not predominate at equilibrium. What will predominate is our carbonyl species, because KEQ is less than 1. Right? That species there is less reactive than our reference point of acid aldehyde. Therefore, we know KEQ is less than 1. Now, let's imagine this. We're going to react with water and acid, and we form our initial hydrate structure. But ultimately, the carbonyl is more stable. So what's going to happen here is we would protonate one of our 2 OH groups. We protonate the unradiolabeled one. O18 would then collapse its lone pair, forming a carbonyl, and then H2O in solution would then deprotonate the carbonyl oxygen, and the net result is the formation of our carbonyl that has a radiolabeled oxygen atom. And of course, we could then form hydrate again, but ultimately, the equilibrium is going to favor the carbonyl, given the inherent reactivity of the carbonyl. So you might be asking yourself, Ryan, what's the big takeaway here? Well, if you're given a question in which you have a carbonyl reacting with radiolabeled water, that's an aldehyde or ketone to begin with. If that carbonyl compound is more reactive than your reference point of acid aldehyde, then we know that KEQ is going to be greater than 1. Hydrate is favored. And when we have a radiolabeled water, the predominant species at equilibrium will be a hydrate with 2 radiolabeled oxygen atoms. If you're looking at a carbonyl that is less reactive than that reference point of acid aldehyde, then we know KEQ will be less than 1, which means that it's not the hydrate favored at equilibrium, but rather the carbonyl. We would generate our initial hydrate, but then we'd have our back and forth equilibrium ultimately favoring the carbonyl, and because of the large excess of water, we're going to ultimately favor kicking out the unradiolabeled oxygen atom and reforming the carbonyl with the radiolabeled oxygen atom. Okay, this is just a hypothetical situation to be prepared for, as I have seen it occur on exams in the past. The key here is the starting carbonyl more reactive or less reactive than acid aldehyde? If it's more reactive, predominant species is the hydrate with 2 radiolabeled O18s. If it's less reactive, predominant species is the carbonyl with the radiolabeled oxygen atom. So coming back to this visual here, we said that more reactive carbonyls form a greater percentage of hydrate. Less reactive carbonyls form a smaller percentage of hydrate at equilibrium. Another visual that we could create that basically conveys that is this. Looking at these carbonyls, the one at the top is the most reactive. Notice the CF3 group is withdrawing electron density. That is the most reactive, and therefore, when it forms hydrate, we will have the largest KEQ. We form the most hydrate at equilibrium, and that's because the hydrate that it would generate is the most stable hydrate of the ones shown. That electron withdrawal from the CF3 group would help to stabilize the lone pair repulsions. It stabilizes the hydrate. On the flip side, if we looked at the least reactive of the carbonyls, this ketone with the terbutyl group, that would form the smallest KEQ. We form the least amount of hydrate there because the hydrate itself is the least stable. We can imagine that the terbutyl group having a lot of steric hindrance to it would just amplify the extent of the repulsions that we already are experiencing in hydrate structure. That terbutyl group would destabilize the hydrate structure, and because it's very unstable, less of it forms. Okay, on a former exam, professors gave a visual like this and basically had students put in carbonyls in their relative energy and then match those to the relative energy of their hydrate structures. And to reiterate, the most reactive carbonyl will form the lowest energy, most stable hydrate, which then forms to the greatest extent. The least reactive carbonyl forms the highest energy hydrate, which forms to the smallest extent. Okay. All right. So now let's do some problems relating to KEQ and relative percentage of hydrate generated. For these two questions here, we're going to use these 5 carbonyls. First question is asking which of them will form the greatest percentage of hydrate, largest KEQ, at equilibrium. Well, we'd form the greatest percentage of hydrate if we were to be looking at the most reactive of our carbonyls. So let's find the most reactive. Here we have formaldehyde. B is an aldehyde with 3 fluorines. I would say B is more reactive than A, so A is not the most reactive. Looking at structure C, that's an aldehyde with 3 chlorines. Chlorine, remember, is less electronegative than fluorine, so fluorine is more withdrawing than chlorine. That means B is still the most reactive so far. Then D and E, notice, are ketones. So with D and E, we'd have inductive donation from the silicon attachment and the other carbon attachments. D and E are probably the 2 least reactive. So based upon this analysis, we'll say that the most reactive of our carbonyl species is compound B, and therefore we'd expect that to form the greatest percentage of hydrate at equilibrium, given that it is the most reactive. I would say that the second most reactive would be compound C. So that would form the second highest KEQ, second largest KEQ. Then if we go to the next question, it's asking which of those compounds will form the smallest percentage of hydrate, smallest KEQ. There we'd be looking for the least reactive carbonyl, because the least reactive would form the least stable hydrate, therefore it would form to the smallest degree. Now we're going to focus on D and E here and differentiate their reactivity. Both are technically ketone functional groups, and the only difference is the presence or absence of the silicon atom. Now remember in the periodic table that we have CNOF, then we have silicon, phosphorus, sulfur, and chlorine. Silicon is below carbon, which means that silicon is less electronegative than carbon. And like carbon, silicon will function as an electron-donating group, an electron-donating atom. So thinking about this with you, we know that to an extent, there's a donation over the carbonyl from this adjacent terp-butyl group, a sigma electron donation, and that would decrease reactivity. If I have silicon instead of carbon, what's going to happen is there's going to be an even greater extent of donation. There's going to be more sigma electron donation from silicon compared to carbon, because silicon, being less electronegative, is more readily going to give up electron density. That is to say, if we used, say, shading here, silicon is donating more electrons over the carbonyl compared to just the carbon attachment. And accordingly, we would say that the least reactive carbonyl is D. Okay, least reactive is D, and therefore D would form the smallest percentage of hydrate at equilibrium, given that it is the least reactive. The second least reactive will be E. Okay. So in other words, if we rank the carbonyls in order of increasing from most reactive to least reactive, let's just write that in here. The most reactive of the carbonyls is going to be B. B is more reactive than C. C is more reactive than A. Then we'd have E, and then D would be the least reactive. Okay. That comparison between silicon and a regular carbon chain, a little bit tricky, which is why I wanted to cover this. Silicon, like a carbon chain, is electron donating, but it would be even more donating than a carbon chain would be. Right? Now we're going to do the same exercise here, ranking an increasing order of hydrate formation. So smallest percentage to largest percentage, essentially smallest KEQ to largest KEQ, which is really saying from least reactive, the least reactive carbonyl, to the most reactive carbonyl. All right. So looking at this first ranking, I see a regular old aldehyde. We know that the methyl group is going to have an inductive donation over the carbonyl. Then with B and C, we're noticing the presence of the CN group. Now the CN group there will function as a inductively electron withdrawing group. So it pulls electron density, increasing the reactivity of the carbonyl. So that means C is more reactive than A, because A does not have the withdrawal that C does. Okay. And when looking at B, there's 3 CN groups, which means that there's 3 sigma electron withdrawal events from a CN group. Accordingly, I would say that B is the most reactive, and therefore would form the largest percentage of hydrate at equilibrium. Then C is the next most reactive, and A is the least reactive. Now, drawing this out for you, why that CN group ends up having a sigma withdrawal is you have this nitrogen that's sp hybridized, and there's going to be a dipole in the direction of that nitrogen, and that provides pretty powerful sigma electron withdrawal. Okay, and certainly if we had 3 CN groups there, there's even more sigma electron withdrawal, increasing reactivity. All right. Kind of funky. One of former exam professors gave structures with CN groups at the alpha position, and that really threw people off. CN groups there would withdraw. We don't think about sterics. We think about the extent of withdrawal. Okay, and if I haven't stated that already, when you're looking at inductive atoms like your fluorine, your chlorine, your bromine, or your CN groups, we disregard sterics and we think more about the withdrawal aspect. And with more withdrawal, there's greater reactivity. All right, this next one, similar exercise, will rank from smallest KEQ to largest KEQ. In other words, we'll rank the carbonyls from least reactive to most reactive. All right, so let's break this down. Looking at A, that's definitely a ketone functional group. And I see this oxygen atom here. Now we know the oxygen atom would probably donate into the benzene ring, and then from the carbonyl, we'd probably expect there to be a withdrawal, although the withdrawal wouldn't be terribly prominent because of how far away the oxygen atom is. Looking at structure B, notice how this is an ester functional group because the oxygen is directly connected to the carbonyl carbon. Accordingly, we expect here for the oxygen to have a resonance donation, a pi electron donation, which would make that less reactive than A. Okay, esters are less reactive than ketones due to that resonance donation over the carbonyl. So we know B is going to be less reactive than A. Then when we're looking at C, that's a ketone as well, of carbon and carbon. And the oxygen is not directly bonded to the carbonyl carbon, right, like it was in B. Here the oxygen is a little bit closer to the carbonyl than in A, and the oxygen atom would have a sigma electron withdrawal effect, and because it's closer to the carbonyl, there would be more sigma electron withdrawal in C than in A. I think that's enough here to say that C is the most reactive, and therefore would generate the largest percentage of hydrate at equilibrium. And then we'll have A, and then B will be the least reactive. B is the least reactive because that resonance donation over the carbonyl directly really decreases the reactivity. Okay, that's an ester functional group. That decreases the reactivity at the carbonyl carbon. With C and A, notice that oxygen atom isn't directly bonded to the carbonyl carbon, so it instead takes on the sigma electron withdrawal effect, withdrawing from the carbonyl. But in A, that is further away, in C it's closer, and because in C that oxygen is closer and withdrawing, it's going to have a greater effect, greater withdrawing effect, right? That's essentially like saying that if you looked at this structure here, fluorine being closer to the carbonyl, that's going to withdraw electron density more strongly than if the fluorine were here. And that in turn would withdraw electron density more strongly than if the fluorine is here. Remember, with inductive atoms, proximity as well as strength can be a factor. And by strength, we might refer to, like we're looking at fluorine versus chlorine versus bromine versus iodine. And with proximity, we're saying that the closer the inductive atom is to the carbonyl, the more its withdrawal would be felt by the carbonyl. That's exactly what we're looking at here with C versus A. I just find that it kind of looks different and feels different with an oxygen compared to a halogen. All right. So a big takeaway here, can't stress this enough, you'll have questions on your exam relating to this. We can essentially ask a reactivity question in disguise, right, by saying which of these carbonyls would form the greatest percentage of hydrate at equilibrium. In any series, the most reactive of the aldehyde or ketones present will form the greatest percentage of hydrate at equilibrium, largest KEQ. And in the series, the carbonyl that is the least reactive will form the smallest percentage of hydrate at equilibrium, smallest KEQ. And a cutoff point that I want you to keep in mind is acid aldehyde. That's an aldehyde with just a methyl group. That is your reference point for where KEQ is greater than 1, where we have enough reactivity to actually favor the hydrate in that equilibrium. And anything less reactive than that reference point, meaning any other aldehyde essentially, with just a simple carbon-hydrogen chain, that would have a KEQ less than 1. All right, can't stress this enough, that visual is so important. Memorize this cutoff and understand that we essentially looked at that trend here, wherein the most reactive form the greatest percentage of hydrate at equilibrium, and the least reactive form the smallest percentage of hydrate at equilibrium. And then we looked at 2 more examples of carbonyls, ranked those in reactivity. The most reactive formed the most hydrate at equilibrium, largest KQ, and the least reactive generated the smallest percentage of hydrate at equilibrium, smallest KQ.